In this video, we will develop some of the basic Excel calculations in relation to sample data. And we will use as an example these 5 data values and consider them to be a sample of values randomly selected from a much larger population of values. Although trivial for such a small sample, we can use the Excel function count, which by highlighting the range of values B2 colon B6 will count the number of values, giving, not surprisingly, the value of 5. For the mean of a sample, we use the Excel function average, again highlighting the range of values, gives us a mean value or average value for these set of 5 values of 80.38. So 80.38 is our best estimate of the true population mean from which these values were randomly selected. In addition to the mean value, it's useful to get some idea of the spread of data values, and we can do that by finding the deviation of each value from the sample mean. So this will be equal to the difference between the x value, take away the sample mean, which for the first value gives a value of 1.02. We now wish to copy this formula to calculate the deviation for all the other data values. When we copy this formula down, the B2 will change to B3, B4, B5, which is good, but the value of B9 will also change to B10, B11, etc., which we do not want. So we wish to lock the value of B9 so it doesn't change, and we do that by putting a $sign in front of it. We can now copy this function, and it calculates the deviations for all of the sample values. It would be useful to get an overall idea of the spread of data values, but if we were just to take the sum of these deviations, we would always get a 0 value because of the way in which they are defined in relation to the mean value. There will also be negative values which cancel out the positive values. So the way forward is to square each deviation, and that will certainly get rid of the negative values. So starting with the first one, that will equal the first deviation squared, which is in Excel up arrow to the power of 2. And we can now just copy this down to get the squared values for all the other deviations. The overall measure of variation in the data then can be obtained by adding up all of these squared deviations, and this is called the sum of squares. So this will be equal to the sum of all of these squared values, 9.13. An important point to raise at this stage is something called the degrees of freedom, which is the amount of information left to perform the calculations. And in this analysis we started with 5 pieces of information, the 5 data values. We then calculated a mean value, so that took away 1 piece of information. So the number of degrees of information left to calculate the spread of values will be equal to the original number of pieces of information, which is 5, the data size, but minus 1. For calculations of spread, we now have 4 degrees of freedom. So with a sum of squares and degrees of freedom 4, we can calculate something called the mean square value, which quite simply is equal to the sum of squares divided by the degrees of freedom, 2.28. We could have arrived at this value directly from the data by using the Excel function for variance. So we could have had equals variance, and we will choose the sample variance, and again identify the range of values, and we get the same value, 2.28. Values of sum of squares, mean squares, and sample variances all have units which are the square of the units for the actual sample values themselves. So to get a more understandable measure of spread, we often use the sample standard deviation, which is then the square root of the sample variance. So we would say equals square root of F9, the variance, so the sample standard deviation of 1.51. It is also possible to get to this sample standard deviation, the spread of values, more directly. We could have entered the standard deviation function, and we would choose the sample standard deviation, and again identify the range of values, and again we have the value of 1.51. So we have the mean value for the sample, and also we have the sample standard deviation, a measure of the spread of sample values. The next step is to look at standard error of the mean. This value is equal to the standard deviation divided by the square root of the number of measurements in the sample, in this case the sample size in B8, of 0.68. Now this value of 0.68 is a measure of the uncertainty when estimating the mean of the population from which this data was derived. So if we were using these sample values to estimate the true mean of the population, we would have the best estimate of 80.38, but an estimate in the error of this value of 0.68. We can now derive something called the confidence deviation, which again is a measure of the uncertainty in our estimation of the population mean, but defining the error as a 95% error range. But before we do that, we must derive the t-value, which is equal to t, and we will use t invert two-tailed, which gives us a two-tailed t-value. For a 95% confidence interval, the probability is 0.05, and we must enter the degrees of freedom for the calculation, which we've calculated in D9. And then the confidence deviation is the simple product of the t-value times the standard error, so that is equal to F4 multiplied by F3, 1.88. What this says is that our best estimate for the true mean of the population from which this data was derived is 80.38, and we are 95% confident that the true value is within the range of 80.38 plus or minus 1.88, giving the overall confidence interval. We could also calculate this confidence deviation directly using the Excel function confidence t by going equals confidence t, and we need to enter a value for alpha, which is the significance level, which for 95% confidence is again 0.05, the standard deviation of the measurement, which we have here in F2, and then the sample size, which is in B8, which again gives the confidence deviation of 1.88.